Welcome everyone to my talk. Today I will be talking about three-body problem of inverse hybrid search. I think it's a very interesting topic. I hope you enjoy the talk by the end of it. Before I get into it, a bit of introduction. So my name is Ravindra Harige. I am founder of Searchplex. I live in Amsterdam, Netherlands. I have a background in artificial intelligence, machine learning, and information retrieval. I have been working on search problems for over 10 years now, and my experience has mostly been building search solutions for specific domains and verticals, and across solving problems across layers of retrieval, ranking, and improving metrics. Um, and because of this interest in solving search problems, I founded Searchplex. So a bit about that as well. We help teams to design and modernize and scale production search solutions. Most of the times, there are different entry points, like either the teams know already where the problems are, then we help to solve and optimize that. But most often, what we are seeing lately is also there are teams who have spent a lot of time over tuning certain their specific search stack, and they are held back in improving it further and specific to the AI workloads. So that's been a good chunk of work where we also help in modernizing the search stack of the teams. Because of the domain-specific search thing, we have worked across multiple domains so far in e-commerce, legal, regulatory, as well as health science, and do all the like three specific areas where, as I said, like is the audit, where we help in diagnosing the issues, or POCs or build solutions, also the modernized part. So do check out the website for case studies and use cases. And yeah, happy to chat more afterwards about that. So before moving into the specific use case, let's set the scene. So you're at home, you're watching a movie, and this is a red notice movie, and you see the ones on the screen, and you're like, oh, I really like the jacket he's wearing, and I want to find if I see a similar jacket to wear myself or purchase. And then you pause the screen, you take a snap, and then you try, you head over to your favorite shopping app, clothes shopping app, and then see if you find something similar. So in this case, you do see something similar, but it's not similar enough to what you are liking. And there do you see a jacket like on the fourth position, which is closer to what you want, but it's out of stock. So what do? You're like, okay, if not now, let me track this. So you save the search, and you expect that the system understands your intent, like you are looking for specific jacket, you're searching for it, and you want to be notified when it enters the system, when new products similar to that enters the system. So that's the saved search use case, or alerts. It's this is not new for us. This is basically we are saying this is the query. If something matches this, let us know. And the notifications can be email or push notifications. And we have seen this kind of alert or saved searches situations across multiple situations, like for job alerts, or maybe you're finding a house and you want to set up an alert if something arrives, some rental opens up in your specific area, or travel alerts if you're tracking the prices. So alerts are familiar, and mostly who have been building search solution and alert system, you would be very familiar with how that's done with Elasticsearch or OpenSearch Percolator. It's very common to use that. But in this specific talk, I'm going to focus more on the saved searches for e-commerce and quite some websites which are apparel shopping websites. You will see this kind of option where you run a search, whether regardless of you find something now or not, you can always save it. And when you save it, you see the confirmation, and you'll keep receiving the emails from them about the matches, new matches. So technically speaking, alerts are inverse search system, and it's a inverse world because for us, search is always like a query comes, user query, and then it is matched against the corpus of documents or catalog. But in the inverse search or the alerts, it's the other way around. You are storing the user query as the corpus, and the new products that are entering the system are the queries. So take a moment to keep that flip in mind, because that's the whole talk is going to be about. So those who have developed anything like this before with Percolator, in general, you would know that this is mostly the lexical queries that are used as alerts. But what has changed is, since last few years, the ability of using vector search, you can also like use the image as the input, just like what I shared the first use case. You want to be able to be alerted. If you can search with images, you also want to be alerted on the images. So that's the change. And it captures richness which are tedious to describe by words, right? Like the fabric, the style, and things like that. So take a moment and tell me, what's your first intuition? How would you solve this at scale? What does it come to your mind when we are talking about image embeddings and doing a search over that? Any answers? Is it cosine, right? Cosine, cool. Also, perhaps, at least this was my intuition when I started with it. I was like, this sounds like an image search, simple vector to vector cosine. And maybe if we want to do it at scale, we might want to use ANN and things like that. So let's call that top K retrieval, where you are searching with a vector across many vectors, and you want to find what's the closest nearest neighbor. And in this kind of systems, there are multiple tricks that engine employs, right, to get you the best nearest closest matching vectors. But in the end, you are really getting at the top K. But we talked about the alerts use case, where every user has set up an alert with an intention to be notified whenever the match arrives. So think of all the users who do not make it to the top K. And that's not a good thing for them, right? So that's why I call that use case as fetch all retrieval. What I mean by fetch all is, we need to evaluate every saved search, which is a corpus, against the incoming query, which is a product. And wherever the matches are happening, how much ever items it's matching, all of them have to be processed for alerts. There is no top K in this situation. And when we say about matching, there are multiple aspects where it has to match. So there is the image vector itself. There's a threshold, how closely it should be matching. There is different types of filters, price, size, and n number of other things. So it's not a simple, yeah, the closest is a filtered match, right? But yeah, there is vectors and there's many other things needs to be evaluated. So to summarize, these are the two contrasting situations. On both sides, you have the vector, and you need to get the closest matching. But there is one contract where you are just asking for the top k. Let's call that the forward search use case. And in the inverse search, you are like, get me everything that's matching. So that's the difference of contract. So what exactly in play when we talk about matching? There can be lexical signals, keywords. We definitely talked about the image embeddings, the similarity threshold. It's very important. You can think that the threshold would be different for each saved search. So maybe if you are into something very unique, you probably want to give a broader threshold so that you get more items. But if you are looking for something more common, you are probably going to give a higher threshold because you don't want to be spammed by many matches. So think of it like every query has a different thresholds. Now we have to satisfy that along with the vector distance itself. And of course, the other constraints which were always there about size, price, whether it ships to a certain country or not, and the scale. So scale is very interesting because here the scale is at the two sides. On one side, you have how many saved searches are there in your corpus, and on the other side, you have how many products are entering your system. So on both sides, you have the scale which needs to be managed by your system. And the last part is the correctness. So the correctness is you have to really get this right for an alert to fire. You don't, because there is an approximation or there is a distance, there's a vector similarity involved, and the other conditions are involved. You don't want to leave out any matches that are not too sure, right? So it has to be, you have to ensure that the correctness is right in the place. So that brings us to the three-body problem. I'll be sharing how this problem can be seen in these three axes. One is the correctness, the second one is cardinality, and the third one is the execution physics of this. To ground this work, I'm very happy to introduce my client here. It's Gem app. They are the marketplace aggregator who have more than 170 million live listing with embeddings. They already support image search for their customers. They are in the vintage clothing and second-hand market niche. So most of their users are very loyal and they are always looking for something vintage, something specific. So so that's the use case. That's the work where we are doing this, and they are already on Elasticsearch, and they already have in production Percolator, an alert based on Percolator. But as I said, Percolator is lexical as of now. And the challenge was to allow the users to save their image search capability that they have shared, they have exposed already, to save it and let the users be notified of the new changes in the catalog. So let's dive into the pattern, technical pattern here. I told you already that they're on Elastic Percolator. I think Elastic has done a really great job here in the sense of abstracting the complexity. It's really cool that to construct a forward search query is the same DSL, and you can use the same DSL to store it and also be notified in the reverse direction if any matches are coming. So in terms of like the function or capability itself, it's pretty cool what Elastic did. But as of today, I haven't seen it working really well or supported even with the vectors in the mix. So it works well for keywords, but we are dealing with vectors now. Now, to solve this challenge, we looked at and started using Vespa's predicate field and ranking. So this is a capability that is not originally designed for percolation. The history of this feature is around the intended use was for the ads, related to the ads. But it has capability to evaluate incoming products or anything based on the Boolean constraints. So by itself, the predicate field is not a vector solution, but that works very seamlessly with the ranking functionality that Vespa provides. So these two capabilities, they work seamlessly with each other, that together you can deliver a percolator kind of solution with vectors in the mix. So what's the solution looks like? At a broadly speaking, you have incoming products, and then you do the predicate matching, which is the Boolean constraints matching. On the third level, you do the ranking for vector similarity scoring. In the end, you have the clean set of the alerts which you want to process. Let's focus on the first body of problem, that's correctness. So as I said, like it's about arriving at the math set, and there is no room for missing out anything that's not, that should be matching, but you're leaving it out. There is no room for that. And since this solution is not percolator by design, like what Elastic did, it means it has a different semantics for constructing a query, as well as constructing the saved search representation, let's call it that. So there's a semantic for that. And the query, which is a product, how you represent that, that's also a separate semantic. So in order to, before you get to the matching side of things, the first thing is you get these two representations correctly. So ensure your query representation, product as a query representation is done correctly, and saved searches is represented correctly with the predicate semantics. Then the second step, I won't say second step, but another important part is creating a golden evaluation set. So it's really important that you come up with enough examples of positives and negatives, what should be matching, what shouldn't be matching, for a given input product query, what saved searches should match or shouldn't match. So this golden evaluation set generation itself is an interesting task, because you can actually use search engine where you have forward search set up already to come up with all types of permutation and combination of filters and create this data set. But it has to be exhaustive, and it has to be enough confidence-inducing set, because all your work is going to depend on this. So once you have done the query representation, saved search representation, you have evaluation data set, then it's a validation loop. You have to iterate, because those are two different semantics. You need to iterate until you have got all the matches and non-matches in order, and your solution, you have a confidence in the solution, like how correctly it is doing its job. And as I said, like if you don't solve this step correctly, there's no point going to the performance or creating a solution around it. So this is a really fundamental and important step to get it right. So let's move on to the second body of problem. That's cardinality. So we have looked at the correctness, which you have to get it right. The cardinality is, we talked about how there's no top k, it has to match everything. So we are familiar with the query per second kind of metrics. In this case, the product arrival rate is the QPS because we're in an inverse world. And cardinality is how many saved searches it matches. And I'll explain how that decides a lot of things in the entire solution. So the more the number of matches, it is going to impact all the downstream tasks. So what is the first thought is like cardinality could be just the corpus size. Perhaps that's an idea, that's an intuition. But there are three axes to that. Corpus size definitely matters. It's the n number of possible matches. But the rule complexity is the second one. You can imagine, like in the saved searches, there will be users who are just being lazy, just take a photo and set up an alert, no other conditions. Then that's the broader search, saved search. Then there can be saved searches where they are giving the range of price, they are giving n number of possible countries it has to ship, or they are giving the size options, which is also multiple values. So the more number of things you are going to add, the evaluation or the complexity itself, the rule complexity is going to matter. The third part is after the eligibility of match or no match is determined, how many matches, how many saved searches it is bringing out of that step. That's the third important part. So cardinality is decided there. And for each saved search, it is doing two types of role. So one is it is carrying all the aspects that we just discussed about lexical, boolean constraints and ranges and everything. But it has to also run all this logic on every incoming query or incoming product. For each incoming product, all this logic has to be executed. So just to reiterate, so top K, this was throughout the work, it took multiple times for us to come to this realization that top K, it's not a top K problem, it is a fetch all problem. And no matter how much we think, we keep coming back to this intuition of like, okay, maybe we just need X number of results. But that's not the case. And that has a effect on how do you characterize the workload. So having discussed there are different aspects that are involved, what is the workload pressure of an inverse search system? It's basically the number of products that are arriving in the system multiplied by all the work it has to do to get to the math set. And this workload pressure is going to matter in terms of the performance, because the more number of saved searches you have, so that's the x-axis here, the more number of results or cardinality you're going to have for any of the incoming product. And the P95 is what is going to decide how much your system can perform, because around at some point you're going to start seeing like the performance bottleneck starts raising if you have not sized for the P95 onwards. And here we are just talking about P95 as a math set size. And we'll come to how this matters further. But match set decides, so cardinality decides the match set decides the payload. So what is the payload in this case? The payload, the bare minimum information we need is the alert IDs. Once you have the IDs, you can do all types of processing for sending out the notification. But you can see like the more number of matches results into more number of search IDs, means larger JSON arrays. Larger JSON arrays means more bytes, and more bytes you have to move across different layers. And that brings us to the third body of problems, that's the execution physics. So execution physics is not something specific for inverse search. It's there also for forward search or any types of search system. But this becomes a bit more interesting. I'll explain why. So what happens in a search system, and this applies also for the forward and backward, it's you receive the query, you have, in Vespa it's called container, but in Elastic it's coordinator nodes, for instance, which takes the query and then fans it out to all the data nodes where the actual logic is performed on the specific data it contains. And then it aggregates, it brings back all that information back in that node. And then from there, it has to combine and merge all that results back to the service. The service has to take that payload and deliver it to the client. So that's the entire flow that happens. So when we think of the performance, quite often we think like, how long the search engine is taking to do a job. But in this case, it's not only an engine time. There is also variable amount of time that is being taken in terms of gathering, scattering, the merge operations, the JSON serialization, deserialization, the wire transfer, because these steps, although they apply in the forward search use cases or a forward search flow, in the inverse search, there is no limit, there's no K. Like in a normal search, you would get all these things for 10 items in the result back to the client. But here you need to get all the matching IDs. So the more number of search IDs are there, it has to move that large amount of payload across different layers, which increases your overall end-to-end latency. And when we are building this kind of service for alerting, for search, saved searches, you are, of course, once you have gone past of the correctness part, you are like, okay, is it performing? Is it doing well? Why is it slow? These are very common questions we'll have once you start doing performance test. And then you will see like, it's not up to your expectation why it's not fast enough. And then the reason is this, because and in order to improve the performance, you're like, let me increase more workers, let me increase the concurrency. Maybe it will increase the performance. Maybe I will have a higher throughput. But then we are again back to the execution physics. Like every system in this case has a knee point. So the concurrency is only going to help you up to a certain point. Beyond that, it will have a diminishing returns. So no matter how much you're going to increase the workers and the concurrency, you may not benefit from the performance gains there. So if you're sizing for this kind of service to work in production, your capacity planning has to be at the tail. And what that means is the strictest match is at the 0. 0 matches for a particular saved search. The worst case is all the matches, which is very likely a bug in your system if that's happening. So you need to account for the range realistically for your kind of saved searches you have. What's the minimum and what's the maximum? And whatever is on the P95 side is what going to decide the sizing of your resourcing and of the service and the performance. So this is the flow that is going to that is sort of perturbation is what I call, like it has a cascading effect, like the broader eligibility brings more candidates has more matches, and more payload size, and more payload size moving around has an effect on the request times, which has an effect on the throughput. And if you're not managing this well, your product arrival rate or QPS is going to start running into backlog risk. So this is where the three bodies is coming together. All three has to be taken into consideration while building saved searches kind of solution. In order to effectively diagnose and build a resilient system where you understand the performance, there is no exception. You need to have a good observability across different layers that we just discussed, so that you know what's the incoming load, where the time is taking to in the evaluation, and where the time is going in building the payload, in which layers, and the movement between it. So that's the very important part. So in the end, how can we think of an inverse search solution? This is a new operating model. If you have always built a forward search solution, always pay attention on the contract. What's the contract? Is it top K? In this case, it's a fetch all. What is the shape? How broad or constrained the saved searches are? What is the workload pressure? Because the more cardinality is going to have more work for your system. In the end, the physics of it, like how much latency it is taking to move the payload across different layers. And to do all that kind of understanding, you need to have good instrumentation. So the orbit, bringing back to the last step, we started with a three-body problem. So the orbit only stabilizes when all the three bodies are measured, and you have a good confidence on if each of them are doing its job well and in cohesion. So yeah, that's it.
We have a question here.
Thanks, that was a great talk. How does all this change depending on the frequency and timing of product updates? So a lot of e-commerce shops, new products might arrive in a big lump at 3 in, or they might arrive throughout the day at certain intervals. If you suddenly have, I don't know, 3,000 new products appearing, they've all got to, you've got 3,000 reverse searches to carry out. How do you balance that for performance and keeping your system up?
So there has to be some understanding of what kind of latency targets we are going to set to service that workload. If you're dropping the entire load directly on the alerting service as it is, then as I said, the execution physics kicks in. So there is only so much you can push through the system. And if it is already the requests are in flight, are in service mode, all the new requests that you're going to send through is going to be rejected by the system, unless you have some queuing mechanism where you can control, like, okay, you received a barrage of the request, but the moment you start seeing rejection, you pile it up and then you send it again, you try again. So those kind of mechanisms needs to be built around that. Yeah.
Thank you.
Maybe a very naive question, but at what point we need reverse search instead of just running the queries that were saved every once in a while, like once per day? Like, is that the question of delivering this like alert that your product arrived in seconds, but I can't really think of use case for that? Or is that the question of like this kind of request will be much more efficient in terms of computational power or whatever than just like stupid approach of running these searches the normal direction?
Yeah, that's a good question. So that's the product question actually, because every company, every product for which this feature is important, it will determine what's the urgency is there. In some cases, like people are really, let's say, tracking in-demand products, and they want to be the first to be notified. They want to be able to buy it quickly. In those cases, it has to be quick when the product arrives. But of course, there are like other cases where it doesn't have to be real time, doesn't have to be immediate. But yeah, it varies. It's a product contract question. Yeah.
One last question here.
Okay, thank you for the presentation. Just one question about the physics problem. If I figure out correctly, in alerting, you don't have the gather problem, so you don't have to gather all your results into 10 best results. So why can't you partition all your saved search? For instance, if you have 1 million saved search, you can put it in 100 partitions and run them possibly in parallel to avoid exploding your context. Is it something possible?
I mean, you need to combine, you need to prepare the final list of alert IDs that needs to be processed, right? So if you are partitioning a large amount of saved searches across different collections, then I think that's a way to manage the load. But in general, the intuition is like, okay, all saved searches are in one place. Query enters, and then you need to bring all these things together, and they are still separated by different data nodes, right? So but somewhere it has to collect all the IDs together to make the payload. But yeah, that's probably possible as well if you split as a separate systems.
Because at the end, the alerts are processed one by one, and you don't have to gather them at one point.
Yeah.
But okay, and just a final question. You showed that GEM, so the use case, used Elasticsearch in the first place. So
yeah,
do they currently use both Elastic and Vespa, or did they switch from one to the other?
So that's a migration process that's underway. We started with this very hairy problem because this was blocking them in the production first. The forward search use cases are known to be relatively easier, but now it's proven that this works great. Then the rest of the work is underway.
Great. Thank you very much, Ravindra.
Yeah.